All righty, folks. How we all doing? How we doing? How we doing? All right. So we come to our final ESA, or not ESA, our final section here in Chapter 8, where we're going to take combinations and kind of bring them together and give them some sort of an application, something called the Binomial Expansion Theorem. So we're going to, first of all, we're going to build up a little bit to it here. It won't take too terribly long. So we had a mathematician back in the 1600s, also a philosopher, a guy named Blaise Pascal, and he had this triangle called, it was nothing really all that big a deal. It was just kind of a pattern of numbers. He basically said, if I start with all these numbers and I start adding them together, I can create essentially numbers that when I add two numbers together, the number that goes directly beneath it is the sum of those two numbers. So if I were to keep ones on the outside and add two numbers beneath it, so these two numbers right here, if I were to add these two numbers, there we are, go green, add these two numbers, the numbers directly beneath it is essentially the sum of the two numbers, the sum of the two numbers. Just like above it, we had the sum of the two numbers, 1 and 1, we add them up together, we get 2. And if we keep doing this down there, Pascal, he noticed this interesting little idea, and it's nothing, not that, honestly, all that mind-blowing, but some really crazy little things kind of came out with it, which end up having some kind of interesting application. And so you can kind of see two numbers that are right next to each other. When you add them up, you get the number directly below it. You get the number directly below it here. So 1 and 2, again, we have 3, 2 and 1, we get 3. And we just can keep doing this little pattern all the way down. Whenever you do that, you just always add more ones on the outside and you do another row. So we'll show this one more time here. So notice 1 and 4, we're going to add, 4 and 6, we're going to add, 6 and 4, 4 and 1. When we add them, you get the number again directly below. Directly below. So we add them and we get the number directly below. So why don't you guys pause the video real quick, see if you can figure out what the next row would be. So the next row of Pascal's triangle, what would it be? I'll wait for you guys to go ahead and do that and then unpause it. All right, here we go. So we're always going to add another row of ones on the outside. So 1 and 5, we add them together, we get 6. 5 and 10 added together, you get 15. 10 and 10, you get 20. 10 and 5, you get 15. And this would be the next row of Pascal's triangle. And again, you just keep this pattern going down further and further if you wanted to. You're just going to see more numbers pop out. So 1, 7, 21, 35, 35, 21, 7. And this is called Pascal's triangle. Well, one of the things that got to be kind of cool about Pascal's triangle is, if you notice here, they started looking at all the different numbers. So they called this one right here, this was called row 0. This was row 1, row 2, row 3, row 4, and row 5. So row 0, row 1, row 2, row 3, row 4, and row 5. And if you notice there, these rows that are the same thing, if you were to use combinations, and so notice the R values on these combinations here, what I wanted. These R values on the combinations, you start at 0 and you count up to the row number. If you notice, they ended up being the same thing as Pascal's triangle. So row 2 on Pascal's triangle was 1, 2, 1. Row 2, so 2, 0, 2, 1, and 2, 2, turned out it also ended up being, with combinations, Pascal's triangle. If we keep doing this all the way down here, here's row 3, 1, 3, 3, 1. We start at 0 and we count up here. 1, 2, 3. Again, with combinations, you ended up getting Pascal's triangle. Again, it's kind of a really cool thing here. So combinations gives us this Pascal's triangles. It just starts popping up all over the place. So there's that 4th row, and here's the 4th row using the combinations. And again, it just pops up. Well, here's what math people saw. They said, okay, well, you know, what if we start taking some exponent, or taking some x plus y and start taking them to exponents. So if we take it to the 0 exponent, anything to the 0 exponent is 1. If we take it to the first exponent, you'd get 1x plus 1y. If you take it to the second, you get 1x squared plus 2xy plus 1y squared. If you take it to the third, you get 1x cubed plus 3x squared y. Take a look at these coefficients. Turns out these coefficients are the exact same coefficients as we had with combinations. They're the exact same thing we had on Pascal's triangle. Here, let me show you again. 1, this is the 5th row, 5, 10, 10, 5, 1. The 5th row with combinations, 1, 5, 10, 10, 5, and 1. And the 5th row for the expanded binomial is 1, 5, 10, 10, 5, 1. Pascal's triangle and combinations and expanded binomials, they were the entire same thing all the way down. And that fascinated mathematicians, and they were able to go ahead and use it then to create, and by the way, we have a little typo here on this. We've got to fix something real quick. That shouldn't be a y. That should be an x. All right. I mean, that shouldn't be a r, it should be a y right there. All right. We have a way to expand a polynomial. Any polynomial or binomial to any exponent, following this idea, what we call the binomial expansion theorem, which is this right here. This is called the binomial expansion theorem. I think the best way to see how this works is just to try it. So we have our first term. Notice, well, let's not say first term quite yet. Notice we are going to start with our combinations. So the n value is always this number right here. That's our n value. So that means our n value is 5. So we're going to start with 5c0. We'll start with r equals 0. And we're going to count up until it's 5, 5. So I'm going to have 5c0. And we're going to add to it 5c1. So every term is going to have 3 parts to it. The first part is the coefficient. So the coefficients come from Pascal's triangle. They come from these combinations. So we count all the way up until we get to 5c5. The next part is we are going to take our first term, and we are going to always take and make its exponent the n minus r, the two exponents subtracted together. And by the way, we should have one more thing here to this little theorem. This whole thing should have been like this, equals so back to the binomial expansion theorem. So we have the green part here, the first term, and notice the exponents are always going to be n minus r. So here's your n and here's your r. So the first term, x, 5 minus 0, it's 5. Your first term, x, 5 minus 1. Your first term, 5c2, 5 and 2. So 5 minus 2 would be 3. 5 minus 3 here, that would be 2. Notice we're just counting down our exponents. So the first term is going to be all the exponents counted down. And the second part is going to be all the exponents are just going to be the same as the r value. So whatever that second term is, they're going to get whatever that r value is for their exponent. So here's my 3. That makes it my second term, or it's technically a positive 3. So positive 3, that was not a 3, it looked like an 8 there. And my exponent is 0, or my r value is 0, so that's my exponent. So where we counted down with the green exponents, the blue ones are going to count up. So 1, 2. If you look at the exponents, notice 5 plus 0, 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus, this will be 3. The exponents will always add up to the n value the entire way. Four and 5. So we're going to plug everything into our calculator, or you can use Pascal's triangle. Doesn't really matter. So 5c0, that's 1, plus 5, plus 10. So we get all these values here, plus 5. And instead of multiplying it all the way out, as you get pretty quick at this, and you will get really quick at this, the binomial expansion theorem allows us to go ahead and do and multiply out these binomials really, really, really quickly. But again, we need combinations to do it. Or you just use Pascal's triangle, which you can do, totally okay. And then 3 to the 0 power, that would be 1 times 3. And when we bring it all together here, we are going to have an expanded polynomial that we can then be able to have in standard form. So x plus 3 to the 5th, when I multiply it all the way out, it would be x to the 5th plus 15x to the 4th plus 90x cubed plus 270x squared plus 405x plus 243. That's the expanded polynomial. So let's have you guys try one of these yourselves. So I have a little pattern here. Why don't you guys try this polynomial here? See if you guys can actually expand it on your own. Let's see if I can move it up just a little bit more. There you go. All right. So take a look at what the exponent is. Go and pause the video and let's see if you guys can do it. All right, let's see how you did. So here's my n value. N is 4. So I'm going to start with 4. So 4c0 plus 4c1 plus 4c2 plus 4c3 plus 4c4. Okay. Now we're going to go ahead and take our first term. Oopsies. Our first term, and its exponent is always going to be the n minus r. So 2x. 4 minus 0 is 4. 2x. 4 minus 1 is 3. 2x. 4 minus 2 is 2. 2x. 4 minus 3 is 1. 2x. 4 minus 4 is 0. And then our last term, which is negative 1, will always have the r as the exponent. So negative 1. The r value is 0, so this is 0. Negative 1. The r value is 1, so this is 1. Negative 1. The r value is 2, so it is 2. 3. 4. So now we go ahead and multiply it all the way out. So we have 1 plus 4 plus 6 plus 4 plus 1. So there's the red values, the green values. So 2x to the 4th, so that's going to be times 16x to the 4th times 8x cubed times 4x squared times 2x to the 1st times 1. And now we get our blue values. Negative 1 to the 0 is 1. Negative 1 to the 1st is negative 1 times 1 times negative 1 times 1. And when we just clean it all up, 16x to the 4th minus 32x cubed plus 24x squared plus, I lied, minus 8x plus 1. All right, hopefully you guys are starting to get the hang of this a little bit. Let's see if you guys can't try this one. Go ahead, pause the video and see how you guys do. All right, let's see how you did. So here's our n value. So I'm going to go 3c0 and then 3c1 and then 3c2 and then 3c3. Okay. First term, that's 3x. And then I subtract whatever these numbers are. So 3 minus 0 is 3. 3x. 3 minus 1 is 2. 3x. 3 minus 2 is 1. And 3x. 3 times 3 to the 0. Here's my second term, positive 4. And its exponent is always whatever the last number is. So 0. 4 to the 1st. 4 to the 2nd. 4 to the 3rd. And notice, once you guys start getting the hang of this, it's a pretty slick way to actually go through and expand binomials, no matter how big they are, to be able to expand them out. So that's a 1 there. So times 27x cubed times 9x squared times 3x times 1 times 1 times 4 times 16 and times 64. So if we were to expand it all the way out, we end up with 27x cubed plus 108x squared plus 144x plus 64. So the binomial expansion theorem is kind of a cool little thing. It just allows us to multiply these out a little bit quicker to get those things that we really want. So how does this work? Well, we understand the idea of expanding it. The last thing we got to be able to do is, how do we get a specific term? A specific term. So the r plus first term is always going to be given to us by this formula. So if I just want one single term, this is the last thing we want. One single term, notice whatever the term value I want, one less than that is the r value I'm going to use. Well, how is this going to work? To begin with, I have a fifth term. So that means 5 is the r plus 1 value. So the r we're actually going to use is 4. So here's my n value, and now I know my r value. So the fifth term in this expanded polynomial is going to be 9c4 first term times x, and now we're going to subtract the exponent, or subtract the n and the r. N minus 4 is 5. And this last term, the 2y, is going to have the exponent that is the last number. So if I were to multiply this out, then we end up getting something that looks kind of like this. 9c4 is 126. Because let's not kid ourselves. Some of these, it just gets just a little bit too long. All right, we don't want to multiply it all the way out if we don't have to. X to the fifth. So if I want a specific term, I don't need to go ahead and expand the entire thing. I can use our quick little formula here and be able to get the actual values that I want, and be able to do it just a tiny bit quicker. So 2016, x to the fifth, y to the fourth. All right, we're just about done here. Let's have you guys try this once yourself here, friends. Once yourself. And once you've tried it once yourself, I think we'll be good to go here. All right, let's see here. There we are. All right, go ahead and pause the video and go ahead and try it. Let's see how I did here. So here's our seventh term. So that means r plus 1 is 7. So r is 6. Okay, so here's our n value. We have our r value. So that means this is going to be 11c6. And if you type in 11c6, you get 462. And then we're going to take our first term, 3x. And we're going to take that to the 11 minus 6 exponent. So 3x to the 11 minus 6 is 5. And if I were to multiply that out, that's 243 to the x to the 5th. You can see why we wouldn't want to have to multiply this whole thing out if we didn't have to. And then our last term, negative 1. And that's going to go to whatever the r value is, which is 6. So that's going to be 1. And multiply it all the way out, we end up with 112,000. Could you imagine doing that many generic rectangles to figure this out? Holy wow, that would take forever. 266 x to the 5th. All right, friends. So that's the binomial expansion theorem. So I'll see you in the morning and we'll talk a little bit more about it, and then we'll go ahead and finish off this chapter. All right, have a good night.